The Empirical Energy Podcast blows open the silent revolution, rewriting the rules of global energy markets. Measured, verified energy is no longer an alternative. It's becoming the gold standard. We dive deep with the producers, traders, consultants, and renegades driving this seismic shift. Step inside the raw mechanics of how verification and blockchain-fueled trading are dismantling the old systems and creating a future where alternative energy doesn't just compete, it takes over. This is the movement of reshaping energy as we know it, bold, unstoppable, and just getting started. Here is your host, Mark Smith.
Hey everybody, it's Mark Smith, host of the Empirical Energy Podcast, and I'm here today where, honestly, we look at the intersection between energy, AI, and blockchain. So I'm here with Jae Yoon. Welcome, Jae Yoon.
Hi, Mark. Thanks for having me.
Yeah, so Jae Yoon is actually a machine modeling. Well, anyway, you say exactly what your title is. How would you describe yourself to your friends and stuff like that?
So when I introduce myself, I say I'm the machine learning engineer from Clean Connect.
Okay, nice. Okay, so what does a machine modeling engineer do?
So I develop the AI models. For me, I'm focused on the vision-based models. So I develop the vision-based models for our company.
Oh, nice. Okay. So what are the challenges that a machine modeling engineer has? Because in our case, we run a lot of these models on the edge, and there's only so much space and compute, on an edge compute, right? So you have that to deal with, plus then speed, how quickly the thing runs, stuff like that. So yeah, describe some of the challenges that a machine modeling engineer has and how you overcome those challenges.
Like when I'm building a new model, it's really updating the model to 0.01%. Like it's updating a very small amount. And also the models we already have, they're very good. So it's really to make that 0.01 difference. So yeah, it's really train the model. Getting a good data set is also important. Like we have our own unique data set. We want to get the best ones out there. So those are all the challenges. And in terms of the speed, we have those edge devices. We need to test them. We need to make sure it's faster. So yeah, it's all those testings, get the new data, retrain the model, and test it. It's that cycle back and forth.
So I know we use a lot of NVIDIA, edge devices, which in and of themselves improve, right? So when we decide, hey, we're going to go to that next gen, which then probably opens up some new opportunities for you because it's faster, maybe has more capabilities. I don't know. What does that do for you in terms of like we go to a next gen? And then, of course, you have the challenge, which would be, what happens if we got a bunch of cameras deployed with older and newer stuff? Like, does it go backwards, forward? Like, how does that work?
So I guess when we have a new device, we need to understand it, right? It could have a different software in it. The hardware is definitely different. The number of CPU, GPUs might be different. Yeah, we have to understand the whole hardware before testing it.
Anyway, so let's talk specifically about like the gas leak model. Okay. And I know, we're always constantly trying to improve that. And, so that it's dealing with all kinds of various conditions, right? As, happens, everything that we're doing is out there in the real world. It's sitting on some site dealing with the elements. It's outside and, has to deal with wind and snow and rain and also just the way gas behaves, right? Because different cuts of methane and things like that. So anyway, I think you brought some examples today and talk about like what some of the challenges are, what you did kind of solve those challenges, and then the results. So I'll go ahead and if you want to queue up your screen, then I'll share that. So I always find it, better in your particular case, you're demonstrating, kind of the end result and like that, in real
hmm
world kind of stuff.
hmm
So yeah, let's talk us through some of these examples of, before and after and what some of the things you had to do.
Yeah, so yeah, let me start with showing some of the videos that I have.
Okay.
Yeah. So as you mentioned, Mark, the one of the difficult things about this gas leak model is, or gas itself, is that it's really hard to see, even with the OGI cameras. They're sometimes very thin, and they don't really have a strict outline. So you need to sometimes move through the videos to see it actually like plumping out or moving. So even on this video, it's on a single screen, on a single frame. It's really hard to see where it is. But if you see it moving, you can see the pluming of the gas.
Yes. Hmm.
Yes. So the new model, we focused on this movement. So we used a new method called channel stacking we've developed. Yeah, I can talk about that later on. So it detects this pluming of the gas and the gas like visually itself to detect it.
And
So
plus,
see,
there's
so
other
the
stuff going on, in the background. I mean, you can see stuff happening above the scene, like back in the field back there, that you have to sort of ignore as well.
yes, so that's what the new method is about. Like it understands the movement of the gas itself and ignores the
Okay.
other stuff.
Right.
So right now the background is not a normal moving of a gas pluming. So
Right.
it's not thinking that's gas. Only this particular part is the gas.
So on the left, is that's like the raw image, and then the right is what we've detected.
Exactly. Yes.
Okay. Yeah, and so you have to look at that particular scene, the video moving over time, and be able to, you know, figure out what the part is that you need to concentrate on, and so on and so forth. Okay.
And here's another video.
Okay.
Yeah. Uh, Same here. It's really hard to see the gas in one image,
Right.
but if you see here, there's some kind of different color, right? There's more texture to it.
Hmm.
That's representing the movement of the gas.
So what were we doing before, and why is
Mhm.
channel stacking the answer?
So what we did before, we used a time series approach. So we looked at a whole video footage and tried to understand what's going on there. But that took a lot of computational power and was hard to set up for a new train. We had a ML ops system that would train the model with the new data coming in, but we hit a wall. The upgrade was not very marginal enough. So we decided to move on to a new way of detecting gas. So we read some papers, tested like 4 or 5 more models, and we finally got this new channel stacking method. So if I elaborate on this method, it's like putting a multiple different frames in different times and putting them together, just stacking them together, like a faint picture on a transparent paper. You just stack them together and you see all those pictures. So that's why we get this different color textures here. I think this video will give you guys a better understanding of how the texture goes.
Hmm.
See this different colors here?
Oh yeah. Okay.
Yeah. So that's representing the movement of the gas. So it's really amazing because instead of just looking at a single frame, we're putting those features of different frames, which we call it a temporal feature, into one image, which is a spatial feature. So the model just looks at one frame and understands both of those features together.
Interesting. And how many kind of frames do you need, or time, if you will, for that to work? Because obviously the longer, then that'd be a lot of stacking.
Mhm.
Shorter might not be enough stacking. What
Mhm.
did you end up? Yeah.
We only have three. We only just need three images, three consecutive images, stack them together, and we get our amazing channel stacking method image.
And are these three like 1 second apart, or like how many? Because yeah, I mean,
Mhm.
if you've got a video, you could be getting X number of frames per second, so you wouldn't even see any movement if it was immediately after. Are you finding? Yeah, how do you find the right three?
Actually, we're using immediately like next frames.
Okay,
Yeah.
so that would assume then that it's fairly rapid movement, right? Which
Mhm.
is, I guess, how gas behaves, or especially methane gas. Okay, interesting. How does the wind play into that?
The win. So our data set is very unique and curated very deeply. So even we have data of different environmental situations. So even when there's like a lot of gas, rain, snow, no wind at all, we have all those data. So it's trained based on all of those data.
Interesting. Okay, so it's got all those edge cases and everything built in. Okay.
Mhm.
Any more examples or
Oh yeah. So this one also is very hard to see.
right? By the way, just out of curiosity, is with our like cooled or uncooled camera? Can you tell? Or does it
No,
matter?
I don't
Okay.
think it matters. Yeah.
Yeah. And that's what we've been trying to say is that really, the only time we're using the cooled is maybe for really far distances or things
Hmm.
like that, or where there's a super, super low cut of methane, like at a refinery or something like that.
Hmm.
What's this? What are we looking at here?
So this is gas coming out from this tank,
Okay.
and it's really fast, and the wind is blowing really fast,
Uh-huh.
but it's still catching it.
Yeah. And
Mhm.
are we introducing this color to it?
Yes.
Okay. And
Hmm.
so what does the color represent? Is that part of the stacking part?
Yes. So
Okay.
it's different times.
Yeah.
So if there's a different color, it's meaning that it has changed through those times.
Okay. Excellent.
If you see the area that has no colors, it's basically they're the same. It's
Yeah.
there's no change in the time.
Interesting. So with this method versus our old, I know you used to call it time series, but I think in some white paper you guys helped write was like the convolutional model or something like that. So
Mhm.
which deals with looking at it over time. What does this new model then allow us to do? Is I would imagine it'd be pretty quicker,
Yeah.
take less, maybe compute power. I don't know. I mean, what are some of the
Mhm.
benefits of this?
Yeah, like what you said, Mark. It takes in a less computation power
Uh-huh.
because with the previous model, we had to look at like a few hundred images to see if there's an actual leak. But right now, we're just looking at a single image to detect if there's leak or not. So it's much faster, less computational power, requires less memory. So our edge devices will not have a hard time using this model. And the accuracy itself, because it's not just looking at movements, it's actually detecting gas and its movements. It will definitely reduce the number of false alarms too. So improving accuracy, less false alarms, and faster speed.
Nice. Well, and that's a big deal because in our case, all of our customers, they're not just running a single model, right? They're running dozens of models on the same edge device, which are all competing for resources and time and things like that. So, yeah, the more models and stuff that it makes it, much. It's a huge benefit to the customers to be able to do multiple things with the same camera package and stuff like that. Excellent. Where do you see kind of computer vision or visual AI going? I mean, because obviously for you, you've been working on this particular problem for, a few years or something like that. I don't know. Has it been that long?
For me,
Yeah.
yeah, I've been working for Clean Connect for like two and a half years now.
So 2+ years. So you've seen various iterations along the way, but based on what you're seeing and where things are going, where do you see this kind of going?
Yeah, I see these iterations. I see improvements. Like when we built an initial model, we see it as pretty good or perfect, but there's always room for improvement. Even for this gas leak model, we're working on attaching a large language model to create like summaries and categorize the events based on like the importance. Yeah, and also like pinging where the based on the results, pinging where the leak is happening, like not just gas leak on zone 3, but gas leak on tank number 4 in zone 3. All sorts of stuff.
If the LLM could identify that component and what that component is, then you have different characteristics, right? So let's just say particular, it's snowing and it's on top of a hot piece of equipment, and you go, wait a second, this might be steam, not gas. So, we're going to say, even though we're seeing something that kind of looks like gas, we're going to say it's probably not gas, but we're making a very, very, reasoned thing because we know what we're looking at. It's not just an image in a screen. It's like, wait, I know what that image is. Yeah.
Yes, yes.
So that's fascinating because it's like augmented reality. I can imagine in the future if somebody could, go out on site. And of course, our main goal is so they don't have to go out on site, right? We can eliminate all those call outs, but we're allowing our clients to see augmented reality, like, see something where it's beyond what they're just looking at the frame. And that human being needs to know, hey, that's a tank, that's a pressure relief valve, but the system knows as well. And what can that do, that object identification do in there? What's that allowing us to do?
Yeah, it's allowing us to really understand what's happening. You know, there's a lot there goes a lot of things in the scene. By knowing all of those, we know what to prioritize. We know what's dangerous, what's like okay. This could really, help a faster response for the customers, cut costs, as you mentioned, all of those stuff.
Yeah. Well, I imagine it would decrease the training time because, before you take somebody off the street and they're looking at those images, they don't even know what it is. Like they may not even know what a tank is. Okay. And then you take someone who's 30 years experience, they're looking, going, oh, I know what this is. Or even someone like Jana, who's, a chemical engineer who may have designed the site. She says, oh, okay, it's doing this because something else down the line. So yeah, I mean, we're just making those systems smarter and, helping out the users. Well, this is great. I mean, it's fascinating for me to watch this, and I'm super proud of what you guys are doing. So anyway, any last thoughts on?
Yeah, I guess like I mentioned, we talked about the channel stacking methodology, and if you need more explanation on it, we've written a paper for ADIPEC this
Oh,
year,
nice.
and
Okay.
yeah, and we got accepted. That's fresh news for me too. So yeah, it's coming. So soon you'll be able to read the paper on it, which will have a lot more technical and detailed information.
Excellent. I look forward to that paper. Thanks, Jae Yoon.
Thank you, Mark.
The Empirical Energy Podcast requires more than a conversation. It takes action, research, and collective wisdom. If today's episode resonated with you, we'd love to hear your insights. Join the conversation and help us shape the future together. We'll be back with more stories, strategies, and real-world solutions that are making a difference for everyone. In the meantime, be sure to subscribe, rate, write a review, and share it with someone you think would benefit from it too. Thanks for listening, and we'll see you on the next episode.